Everyone, this is part 1 of rational functions in chapter 8-5 of your textbook. These 3 videos are going to be very important because this is probably going to be the hardest part of the graphing for the entire year, so it's extremely important that you take notes from these videos and really rewatch them if you have any problems and ask me questions in class. Okay, so this first part is just out of your book. A rational function is a function whose rule can be written as a ratio of 2 polynomials, and its parent function is 1 over x. This shape of a graph is called a hyperbola, and it has 2 separate branches, and we'll talk more about that in chapter 10. So like log and exponential functions, rational functions may have asymptotes, and the function f of x equals 1 over x has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. So you can see in this picture here the vertical asymptote in green, that's x equals 0, and then the horizontal in red, that's y equals 0. The rational function f of x equals 1 over x can be transformed by using methods similar to those used to transform other types of functions. So we will be doing transformations on these as well. So you can see here, this is the transformation form for rational functions. A would be how much you're stretching or compressing. In other words, what you're multiplying the y values by. And just like before, we have this set up as x minus h, so that way it always looks the opposite of what it's doing. As far as the x values, it's going left or right. So if we saw x plus 3, that would mean we're actually moving to the left 3. If we saw x minus 3, that means we're going to the right 3. And then this plus k at the end, that's for the y values, and that's moving it up or down. So let's look at this parent function. To graph f of x equals 1 over x, we'll use the following parent points. So you can see we have negative 1/4, so 1 over negative 1/4 is negative 4. Or later on, if we have 1 over negative 2, that's negative 1/2. And then we have the positive values as well. That is not supposed to be a negative 1/4, that is supposed to be a positive 1/4, just in case you were wondering. Okay, and so this is it graphed, and so you can see I've got 5 points here. And so my domain for this will be the set of all real numbers where x is, well, if you can see here, I can use any of these x values and any of these x values except for 0. So x cannot be equal to 0. And you may be wondering, well, why is that? Well, if you plugged in 0 for x into 1 over x, you'd have 1 over 0. And we cannot divide by 0 as that is undefined. So that's set builder notation. If you wanted to do interval notation, you could go back to the negative infinity to 0, but we're not including it, union 0 to positive infinity. So either one of those, set builder and interval notation. For the range, for the y values, again, we're going to have all real numbers except for when y is equal to 0. And even though that doesn't mean that x is necessarily 0, there's not a number that we can take 1 and divide it by and get 0. So that means that y will not equal 0. And the set builder notation would look just the same for the range. And then for the asymptotes, we already looked at those a moment ago. But we have 2 asymptotes, and we have a vertical one and a horizontal one. So we've got vertical asymptote, and then we've got this horizontal asymptote. So this vertical asymptote is an x equals 0, and then that horizontal asymptote is y equals 0. Sorry, that's kind of hard to see. It's x equals 0 and y equals 0. So there's a couple of things to consider. Why is it that we have two pieces in this graph? Other sides, we've got this right-hand side, we've got this left-hand side. Well, x cannot be equal to 0, which is why we have that vertical asymptote. So that will split it into 2 pieces right away. And then also, why is the range y not equal to 0? Listen carefully to this. If x is positive, then 1 over x is positive, like we saw up here. If x was positive, then it's 1 over x, or f of x is positive. And if x is negative, 1 over x is negative. But we are never equal to 0, which is why we have the horizontal asymptote y equal to 0. You may want to rewind that and listen to that again if you need to, but let's keep going from here. This is example 1 from your textbook. Transforming rational functions. Using the graph of f of x equals 1 over x as a guide, describe the transformation and graph each function. So you can see in each of these graphs that the blue graph is our parent function, as it has those 1, 1, and -1, -1 points. So if we are looking at 1 over x minus 3, that minus 3 means we are moving it to the right 3, so we take each and every point and move it to the right 3. And notice that even the asymptote moved to the right 3. What used to be at x equals 0 is now at x equals 3. But moving it to the right 3 didn't move anything up or down, so the horizontal asymptote stayed at y equals 0. For part B here, we have 1 over x, then minus 2. That minus 2 is not with the x, that means it's for the y values, and we're going to go down 2. So from our parent function in blue, we're going to move every point down 2, including our horizontal asymptote at y equals 0. It got moved down 2 as well. Let's look at a couple more examples. Okay, so I've got 2 examples here. This first one is 2 over x minus 2 minus 3. And I'm looking for the domain, range, and asymptotes, and we're also going to graph it. So first of all, let's talk about the transformations that are happening here. This minus 2, that means we're going to the right 2. And then as far as the y values go, this 2 on top means we are going to stretch it vertically. So stretch vertically by a factor of 2. And then finally, this minus 3 means that we're going to go down 3. So one way you could do this is to start out by putting your parent points on the graph. I guess I should make that, let's fix that, oops. Okay, fix those points. We've got a fourth, 4 1/2, 2, 1, 1, 2 1/2, and 4 1/4. And then the negative side, let's put that on there as well. Okay, so those are the parent points. And you could sit there and take each individual point, move it to the right 2, stretch it vertically by 2, so multiply the y value by 2, and then move it back down 3. Another way that you could do this is to start out by putting the asymptotes on the graph first, which is what I think is a little bit easier. So let's go ahead and do that first. So we'll put the asymptote in blue. Okay. So for the vertical asymptote, that will move whenever we're moving left or right. So we've moved it to the right 2, and I'm just going to use a squiggle line here. So there's our vertical asymptote now. And ignoring the fact that anything got multiplied, the horizontal asymptote moved down 3, so that will move down 3 from 0. So the reason that this can make it easier is we can pretend like this point is our new origin. So we could pretend like that is now 0, 0. And then if we knew where the parent points were, once you've got those memorized, in relation to this new origin, all we would need to do is stretch them by 2. So that's what I'm going to do. I'm going to say, okay, we had a point at 1, 1, but we would stretch that y value by 2. So now it's at 1, 2. We had a point at a half 2, but now it's going to be at 4. And again, I'm counting these y values and x values all based off of the intersection of my asymptotes. I had a point at 2 1/2, but half doubled is now 1. And I had a point at 1, 2, 3, 4 1/4, but fourth doubled is now a half. And then I guess we could also do this one too. The 1/4, 1, 2, 3, 4 doubled is now at 8, 5, 6, 7, 8. So sorry, I went out of order there a little bit, but there are all of the 5 points. And then do the same thing with the other side. We were at -1, -1, but -1 doubled is now at -2. We had -1/2, -2, but now it'll be at -4. We had -4th, 1, 2, 3, -4, but now it'll be at -8, which is way off the graph. And then we had 2 1/2, -1, I'm sorry, -2, -1/2, doubled is now at -1, and 1, 2, 3. So we had -4, -4, now doubled is at 1/2. And so there was another point way off the graph. But here is the new graph. It's been stretched, it's been moved to the right and down. Okay? So again, you could put the asymptotes on there and then pretend like that's the new origin and then do the stretching, or you could put the parent points on there and move every single point, up to you. For the domain, that will be the set of all real numbers where, and we just have to look at where the asymptote is. X cannot be equal to, and our asymptote is at 2, so X cannot be equal to 2. And then for the range, that'll be the set of all real numbers where's our asymptote at? It's at -3. So Y cannot be equal to -3. And we've already mentioned where the horizontal asymptotes were and the vertical asymptote. So the vertical asymptote, that's at X equals 2. And the horizontal asymptote is at Y equals -3. So notice that the horizontal asymptote and the range, same numbers. Vertical asymptote and the domain, same numbers as well. Okay, so what I would like for you to do is try to do this example 2 on your own. And then we'll do that whenever you get to class tomorrow. Alright, I'll see you then. Please let me know if you have any questions. It's important to get them answered now, as tomorrow we're going to go into a lot more detail and a lot more examples. Alright, I'll see you tomorrow. Bye.